In this lecture, we'll introduce an important data structure used in many computer designs. We'll then talk about how we implement subroutines in our assembly programs or functions in higher level languages. And we'll introduce a couple other related instructions, specifically the JALR and JAL instruction and a couple pseudo instructions. But first, let's talk about the stack. So many of you have probably seen this type of data structure before. It's an abstract data type that has this property that the last data in is the first data out. Usually stacks have two main operations, pushing and popping, putting data onto the stack and popping data off of the top of the stack. An important thing to note here is that the stack is really just a place that we store things. It's just a chunk or a segment of the memory that we're going to use in certain situations. There are both hardware and software implementations. For our Otter machine, much of the management of the stack is going to happen in our assembly program. And as we'll see shortly, one important use of a stack is for allowing machines to support functions and subroutines. So let's look at how a stack works. So on the left here I have an empty stack. There's no data in it. But then when I push the number 34 into the stack, it's going to go to the top of the stack, in this case at the bottom of this array. Then when I push 3 more values, those 3 most recent values are pushed onto the stack, and the 34 value is pushed down, or moves up in this case. Then if I want to pop data from the stack or remove data, when I do a pop, I'm going to get the last data that was pushed onto it. In this case, it was a 17. If I do 2 more pops, I'll take off those last 2 pieces of data, and now I'm back to having just 34 at the top of my stack. So this is one way that we could implement a stack. However, it's not very efficient, especially when we want to put it in hardware, because I'm going to have to shuffle or move the values around every time I push and pop. For this reason, instead, rather than shuffling the data, we're just going to move the top of the stack, or as most machines call it, the stack pointer, or SP. So again, on the left here, my stack is empty, and the stack pointer is pointing to a default value. When I do the push, I'm going to increment the stack pointer to point to the next location. I'm going to decrement the stack pointer to allocate a new spot on the stack, and then write the value 34 into the memory. The same thing occurs when I do 3 more pushes. I move the stack pointer up 3 more addresses and put in those 3 pieces of data. Notice that it's the stack pointer that's constantly changing, but is always at any moment pointing to the last element on the stack. When we want to pop or remove data from the stack, we simply move the stack pointer down, or we add to it. So these are the basic operations for the stack, pushing and popping, and we manage it through the stack pointer. And the stack could be used, we'll see shortly, for different types of applications, including it could be used to support functions and subroutines. So a quick recap on control flow in our program. Remember that normally our machine just executes instructions in the program sequentially. And this is the reason why the PC, for the most part, is just incrementing. But in order to more easily create complex programs, we also have some special instructions that we can use to modify the control flow of our program. Or in other words, load other non-sequential values into our PC at different points in our program. And we've already seen some of these. So we've seen jumps, or unconditional branches, and also the conditional branch instructions. And now we're going to talk some more about another important construct for control flow related to subroutine or functions. Okay, so say we have a program, shown here in the bottom left, where we frequently do the same sequence of instructions. So I have some code, a block A here, and then I have a block X, I do something else, and then I do X, and so forth. The idea being that this sequence of instructions, X, is repeatedly done in my code. An example sequence like this that we've already seen in class would be something like the loop that does a multiplication. Maybe we have a program that does multiplication several times. Instead, what we could do is write those sequence of instructions for this X block just once, and whenever we need to execute it, we're going to change the control flow to come to this location in the program, execute X, and then when it finishes, come back to the next instruction. So as you can see then, subroutines are a nice way that we can not only reduce the space in memory that's taken up by our program, it also makes our program more readable, easier to maintain and debug, and also reuse, supporting a modular programming approach similar to the modular approach which we've taken and 133 with hardware design. Okay, in general, there are 6 important steps when we call a function. The first thing that has to happen is that we have to put the parameters for the functions in a place where the function can actually access them. Then we need to transfer control to the function. Essentially, we're going to jump to the function. We may then need to acquire some local storage that's needed for the function. Then we actually perform the code or the task of the function. If the function then has a return value, we're then going to put the return value in a place where the calling code can get access to it. And the function also, at this point, will restore any registers that it changed or used, and were also being used by the calling code. And then the last step, an important one, is that we're going to return control back to the point where the function was called, specifically to the next instruction. And this is important because there can be several points in the program where a function could be called from. Okay, for RV32I, there are some function call conventions, which I would recommend you get in the habit of following. Of course, it's your machine, you're designing the hardware, and you can design the software many different ways. In general, as we've discussed before, registers are much faster than memory, and the ISA, RV32I, takes advantage of this to optimize functions. For functions with 8 or less arguments, they can use some of our general purpose registers, specifically x10 to x17, to pass parameters, as well as return values to and from a function. And you can use these names for the registers A0 to A7 in your programs and are equivalent to x10 to x17. We also are going to use the register x1 for a special purpose here, and that is that it's going to be our return address. In other words, this is the point that we're going to return to after the function is over. And you can use the symbol RA in your program to reference this one. So let's look at an example. Let's say I have the following function in C. It takes 2 arguments, 2 integers x and y. It adds them together, and the return value is just the sum. So let's assume that the 2 arguments from the main program, the calling program, are in registers S0 and S1, 2 of our general purpose registers. So the first thing I'm going to need to do before I can actually call or jump to this subroutine is set up the arguments for the function. So I'll move S0 and S1 into the argument registers A0 and A1. I'm also going to need to set the return address before I jump to the subroutine. And if the next instruction is my jump to the subroutine, I'm going to want to return to the address 1016. So I'll load into the return address that value. Then I jump to my subroutine somewhere later in the memory. I'm going to add the 2 arguments A0 and A1 and put the result, the return value, also in register A0. And that's basically all that's happening inside this simple function. It's just adding those 2 values. So then I'm going to return and go back to the right location, in this case the return address, and I'm going to use a pseudo instruction here, JALR, jumping to the register, or more specifically jumping to the address stored in the register RA. So why couldn't I just use a jump here? Well, remember, subroutines could be called multiple times and from different locations in the program. So I can't hard code the jump back to the location because I'm not sure during execution where this particular function was called. I'll know during the execution, but not statically or at the time when I'm compiling my program. So this is the reason why I have to jump to the value in the return address. Okay, so the ISA also has an important base instruction called JAL, and it stands for jump and link. And it's a handy instruction because from our previous example, we had to load into the return address register the value and then jump to the location of our subroutine. The JAL instruction does both of these. So in our previous program, we could have done a JAL to label sum. So in addition to making the common case fast, because many programs have function calls, we're also reducing the program size. And an additional benefit is that we don't actually need to know where the code is in memory for subroutine calls. So this is an important instruction, the jump and link. There's also a handy pseudo instruction that we'll use called call, and it does what you'd expect, which is basically the jump and link operation. For returning from a subroutine or function, in addition to the JR pseudo instruction, there's another handy pseudo instruction called RET that we can use at the end of our subroutines.